This is the 17th video in a series devoted to introductory proofwriting. In the previous video, we looked at relations on sets, as well as some certain characteristics that those relations can satisfy. And today we're going to look at a special type of relation known as an equivalence relation. So the definition goes like this. A relation R on a set A is an equivalence relation if it is reflexive, symmetric, and transitive. Recall, those were the properties that we studied last time. Then there's kind of an accompanying definition that goes along with this, which is the notion of an equivalence class. So given that R is an equivalence relation on A, and we have an element, little a, from A, the set, which we'll denote by bracket A, which is the set of all x in A that are related to A. So notice I've got x in A such that x are A. That's said to be an equivalence class with the equivalence class representative A. So I want to look at some basic examples first before we prove some properties, and then look at some more maybe classic examples. So let's take our first set to be -1, 0, 1, 2, and we'll look at the following four equivalence relations and kind of compare and contrast them. So let's say our first equivalence relation is just simply equality. So that means that things are equivalent, or they are related if and only if they are equal to each other. So what does that mean? That means that we can write R as the following set. So it'll be -1, -1. So that means -1 is related to itself, 0, 0, 1, 1, and 2, 2. So recall that R was really a set of ordered pairs of elements from A to B. It was from the cross product of A with itself. And an ordered pair was in the relation if and only if they were related. That was sort of the idea here. So this says an element is only related to itself. Okay, so now let's look at the equivalence classes. Well, notice the equivalence class of -1 will simply be the singleton -1. That's the only thing that's related to -1. Furthermore, the equivalence class of 0 is just the singleton 0. The equivalence class of 1 is simply the singleton 1, and the equivalence class of 2 is simply the singleton 2. So we can definitely have equality be an equivalence relation, but I would say it's not super interesting. And that's because it doesn't really filter anything out. The whole idea behind an equivalence relation is you want something slightly weaker than equality, so that you can study a set without looking at maybe exactly the specifics. But equality is almost too strong to do that, because if we look at the set of equivalence classes, we've essentially just reproduced the original set. Okay, so let's look at our second equivalence relation, which is two elements are equivalent if they have the same parity. Let's recall that that's the same thing as them being congruent mod 2. So what things are in this set? So here we would have R is equal to -1, -1, and -1, 1. So -1 is related to itself because they have the same parity, and -1 is related to 1 because they have the same parity. And then furthermore, we would have 1, 1, and 1, -1 by reflexivity for 1 and then reflexivity for -1, 1. Okay, so that would be everything with an odd parity. And then we also have relations between 0 and 2. So 0 is related to 2, 2 is related to 0, 0 is related to itself, and 2 is related to 2. So that would be everything in that set. Okay, so notice that ordered pairs exist if and only if the two entries have the same parity, which is exactly what we want. But now let's form the equivalence classes. So the equivalence class of -1 will be the set containing -1 and 1 because they have the same parity. whereas the set containing, or the equivalence class of 0 would be the set containing 0 and 2, again, because they have the same parity. Let's also notice that this top one is the equivalence class of 1, and this bottom one is the equivalence class of 2. That's why I use this word equivalence class representative. Notice this equivalence class containing -1 and 1 has two representatives, -1 and 1. And likewise for this equivalence class containing 0 and 2. So here we have, given ourselves some simplification of the original set. So instead of looking at each element individually, we're looking at each element depending on its parity. Okay, so let's look at our next one, which is things are related if and only if they have the same sign. And here we'll consider negative numbers, positive numbers, and 0 to be three different signs. Okay, so what would our set for our relation look like? So -1 is related to itself, but -1 is not related to anything else because that's the only negative number. 0 is related to itself because 0 is not negative or positive. And then we have 1 is related to 1, 1 is related to 2, 2 is related to 1, and 2 is related to 2 because those are both positive. And then we have to have reflexivity and symmetry in there. Now we can build our equivalence classes. We've got an equivalence class for -1, which simply contains the singleton -1, equivalence class for 0, which is just the singleton 0, and then the equivalence class for 1, which is the set containing 1 and 2. So here we have three equivalence classes. We have filtered our original set slightly differently as to above, but we have given some simplification if we're interested in studying the sign of an element from our original set. So which one of these is better kind of depends on what exactly you're trying to do. Okay, so now let's look no restriction. So by no restriction, I mean everything is equivalent to itself, which means R is simply equal to A cross A. So this will be quite big. Notice we'll have 4 times 4 entries here, so we'll have 16 total entries. So we'll have -1 with -1, -1 with 0, -1 with 1, and -1 with 2, and then so on and so forth. So everything is related to everything else. So in this case, you would have a single equivalence class, and you can take any of the numbers as the equivalence class representative. I'll take -1. So the equivalence class for -1, like I said, will be everything, -1, 0, 1, and 2. And now, whereas this original one was almost too restrictive, it didn't filter the original set in a way that we could study it more simply. This filtering down here is almost too generous. Notice it made everything equal to each other, so that doesn't help us studying anything either. So I think the takeaway here is an equivalence relation and the corresponding equivalence classes are ways to filter sets into smaller parts depending on the conditions that you're trying to study. So like in this case, we would want to study the parity. In this case, we would want to study the sign, and we have these nice simplifications for parity and sign. Okay, let's keep going. Okay, so let's look at another example. Let's define a relation R on R by X is related to Y if and only if sine of X is equal to sine of Y. Now, let's look at some equivalence classes. I won't check that this is an equivalence relation. I think it's pretty clear given that our relation is really defined out of this equality right here. Okay, so let's look at the equivalence class of 0. And this will be aided by the fact that sine of 0 is 0. So hopefully everyone remembers that from having taken a trigonometry class in the background. Okay, so this needs to be all numbers x such that sine of x equals 0. Well, really it's sine of x equals sine of 0 by this rule right here. But because sine of 0 is 0, we get just the solutions to the equation sine of x equals 0. But this is exactly the integer multiples of pi. We have negative 2 pi, negative pi, 0, pi, 2 pi, and so on and so forth in both directions. Now there's a fancy way to write that if you're psyched, and that would be something like this. It would be pi times z. So that's a way of writing every integer multiple of pi. Okay, now let's look at pi over 2. And let's keep in mind that sine of pi halves is equal to 1. So it'll be useful to know that for this problem. Okay, so that's going to be all real numbers x such that sine of x equals sine of pi over 2, but sine of pi over 2 is 1. Okay, nice. So when is sine equal to 1? Well, it's pi over 2, and then it's pi over 2 plus 2 pi, which is 5 pi over 2. And it's also pi over 2 minus 2 pi. What we'll use there is the periodicity of sine. So in the end, you'll get the following set. So we have pi over 2 in the middle, 5 pi over 2 is next, and then before that is minus 3 pi over 2, and then you can get the rest of them on either side by adding or subtracting pi over 2 as needed. Now we can write this in set builder notation if we want, like this. So maybe it would be everything of the form pi over 2 plus 2n pi, as n runs through all integers. I think that would be a good way to write it. And I guess likewise, you could write everything up here as 2n pi as n runs through all integers. Sorry, this should be just n pi as n runs through all integers. And taking inspiration from this sort of fancy algebraic way of writing this set, we could do the same thing down here. It would look like pi over 2 plus 2n times integers. Okay, nice. But we can actually make a picture of what's going on here. So let's recall the graph of the sine function. So obviously it's like periodic like this. And let's go to an arbitrary x. Let's say our arbitrary x is right here. Good. And now what we'd like to do from there is find everything else in the equivalence class of x. So that means we need sine of x to be sine of the other thing. Well, we can get that just by drawing a horizontal line at this point right here, which is sine x, and look at all the intersection points. So all of these things that are green dots, along with the original yellow dot, are the equivalence class of x. So let's maybe point that out. So this thing, all of these are in the equivalence class of x. Okay, let's do another. Next up, we're going to look at an interesting equivalence relation on the set z cross n. So in other words, we're comparing ordered pairs where the first entry is an integer and the second entry is a natural number with other such ordered pairs. So we'll say that a comma b is related to c comma d if and only if ad equals bc. So this has a really nice result. So I'll first show that this is reflexive. So let's notice that a comma b is related to a comma b because a times b is equal to a times b. That's really all there is to it. Next up, let's notice that if a comma b is related to c comma d, that tells us that AD equals BC, but now flipping that, we see that CD is equal to AB, which is the same thing as saying that C comma D is related to A comma B. So that gives us our symmetry. Now let's prove our transitivity. So let's suppose that A comma B is related to C comma D and C comma D is related to E comma F. So that gives us two facts. That tells us that AD equals BC, and it tells us that CF equals DE. Nice. Okay, so now let's take this one and multiply it by A. So let's see what that leaves us with. We'll have ADE is equal to A times C times F. But now we can write ADE as BCE. So let's do that. This is the same thing as BCE, given this fact right here. But now putting that together, we have ACF equals BCE. But now we can cancel C from both sides of this equation, and that gives us AF equals BE. But that's exactly the condition that we need for AB to be related to EF. And you might be worried right here at this step where we canceled C or divided by C. And you would be right to worry about that because C is allowed to be 0. So this step right here can only occur if C is not equal to 0. So in fact, you'd have to repeat this in the case that C was equal to 0 to finish the thing off. But I'll let you do that on your own. Okay, so that's a sketch of transitivity. And then we have reflexivity and symmetry. Okay, so now let's look at some equivalence classes. So let's look at the equivalence class of the ordered pair 1, 2. So that's going to be all ordered pairs AB such that AB is related to 1, 2. But let's recall, what does it mean for AB to be related to 1, 2 by our given? So that means that 2 times A is equal to B. So in the end, that'll give us everything of the form A comma 2A, as A runs through all natural numbers. So we get something like that. Okay, but that gives us a motivation of how this should be interpreted. So this equivalence class we can interpret as the number 1/2. And that motivation comes if we write out what this equivalence class looks like. So this looks like the set containing 1, 2, 2, 4, 3, 6, so on and so forth. But those are all, well, other than 1/2, those are all non-simplified versions of the fraction 1/2. So notice 2/4, that's the same thing as 1/2. 3/6 is the same thing as 1/2, and so on and so forth. So in fact, that's what you're getting for these equivalence classes. You're getting some notion of the fraction A over B. And we can see that by recalling the following rule about fractions. A over B equals C over D if and only if AD equals BC, which we can just get from cross multiplication. So really, this is a nice way of building the rational numbers out of the integers and this equivalence class, equivalence relation setup. Okay, let's move on. So our next little goal is to prove some of the standard general results involving equivalence relations and equivalence classes, starting with the following. So let's suppose that we have R, which is an equivalence relation on a set A. Then what we'll show is that the equivalence class with equivalence class representative A is equal to the equivalence class of B if and only if A is related to B. Okay, so let's get to it. So let's do this forward direction first. So let's suppose that the equivalence class of A is equal to the equivalence class of B. Okay, then let's note that A is related to itself by reflexivity, but that implies that A is an element of the equivalence class of itself, which is equal to the equivalence class of B. But then taking out the middle, that tells us that A is an element of the equivalence class of B. But then by the definition of the equivalence class of B, that means that A must be related to B. And there we've done it. We've done the forward direction. Okay, so now let's do the reverse direction. So let's suppose A is related to B. And notice that we want to show a set equivalence here. So since we want to show a set equivalence, we need to show that equivalence class of A is a subset of equivalence class of B and vice versa. We'll only do one direction because this is a symmetric argument. But that being said, technically you need to do both. Okay, so we'll also suppose that X is an element of the equivalence class of A. And notice where we'd like to go is to show that X is an element of the equivalence class of B. And that's because that will show us the equivalence class of A is a subset of the equivalence class of B, which is like 1/2 of the argument that we'll take to show they're equal. So if X is in the equivalence class of A, then that tells us that X is related to A. But then by transitivity, X is related to A and A is related to B, which means X is related to B. Oh, but if X is related to B, then that's exactly the condition for X to be in the equivalence class of B. Okay, so what did we do? We started with X's in the equivalence class of A, we ended with X's in the equivalence class of B, so that means the equivalence class of A is a subset of the equivalence class of B. And then maybe similarly, the equivalence class of B is a subset of the equivalence class of A, and thus they are equal as sets. Okay, so now let's introduce another definition which is going to be kind of dual to the notion of an equivalence relation and equivalence classes. So for our next definition, we're going to look at the notion of a partition of a set. So a partition of a set A is a collection of non-empty subsets of A. So there we've got a subset of A which is non-empty, such that if we take the union over this whole collection, we get the entire set. And if we take the intersection of non-equal sets, we get the empty set. So they're disjoint. Okay, so let's look at some examples, starting with a very simple one. So let's take A to be the set 1, 2, 3, 4, 5. So this would be an example of a partition of A. We could have the singleton 1, we could have 2, 3 together, and then we could have 4, 5 together. So that's an example of a partition. You could get another partition, maybe 1, 2, 3 is together, so 1, 2, 3. And then maybe 4 is by itself and 5 is also by itself. As you can imagine, there's probably a lot of partitions, and there are a lot of partitions. In fact, they're related to something called the Bell numbers, if you're interested in looking that up. Then we could take integers z and we could partition them a number of different ways. We could partition them into even numbers and odd numbers. So there's the set of all evens and the set of all odd numbers. You could also partition them into the set of all multiples of 3. So that would be 0 plus minus 3 plus minus 6. And then the set of all multiples of 3 plus 1. So that would be 1, and then 1 plus minus 3, and then 1 plus minus 6, so on and so forth. And then the set of all multiples of 3 plus 2. So that would be 2, and then 2 plus minus 3, so on and so forth. So that would be an appropriate partition. Okay, so now let's prove a nice result that fuses together these notions of partitions and equivalence relations. Now we're going to prove a really classic result. Actually, it's the first half of a classic result. The second half will be left as a homework problem. So let's suppose R is an equivalence relation on a set A. So what we'll show is that the set of equivalence classes of R is a partition of A. So that means by the definition of partition, there are two things to check. First, that these union to the entire set, and second is that equivalence classes are either equal to each other or disjoint. So let's prove this first part first, that they union to the whole set. So let's really spell out what we need to prove here. So what we'd like to prove is that the union over all A in A of the equivalence class of A is equal to A. So something like that. So I'd like to point out real quickly that the inclusion in this direction is totally trivial. And that's because each of these equivalence classes is a subset of A. So if we're taking the union of subsets of A, we get a subset of A. So that means all we'll focus on is the reverse inclusion. That is, we'll take an element from A and show that it's in this union. But that's also fairly quick. So let's suppose that we have an element, maybe I'll call it little x in A. Okay, but then by reflexivity, we know little x is related to itself, but being related to something is exactly what it takes to be in the equivalence class. So that means X is in the equivalence class of X. But now the equivalence class of X is most definitely part of this union since X is in A. So this is a subset of the union over all such equivalence classes. But let's see what we've done. We have started with X in A, and we have ended with X as an element of this union. But that tells us that A is a subset of this union. But since this other direction was clear, this is all we needed to show to prove that these union to the whole set. Okay, so now let's move on to this second need, and that is to prove that these are either disjoint or they are equal to each other. And we'll do this by first supposing that we have two that are unequal. So let's suppose we have A and B in capital A such that the equivalence class of A is not equal to the equivalence class of B. And then we want to show that they're disjoint, and we'll do that kind of by a contradiction. So let's take an element X from their intersection. So this is how we're moving towards a contradiction. We'll show that no such X can exist. Okay, but notice that means that X is in the equivalence class of A and X is in the equivalence class of B. But that tells us that X is related to A and X is related to B. But then by the transitivity property of equivalence relations, that means that A is related to B. I guess we're using symmetry on this one first to get A to the left. But now if A is related to B, that means that the equivalence class of A is equal to the equivalence class of B. But that's a contradiction. So that contradicted our assumption right here. So that means that it must in fact be impossible to choose such an X. So let's point that out here. No such X exists. But the only rule that X satisfies is it's in this intersection. But if there is no such X in the intersection, then that means that this intersection is indeed empty. But that's exactly what we needed to do. Okay, so let's finish with one more thing. Now we're going to look at the integers modulo n. And so what is that? Well, we'll denote it by z subscript n. Read that zn. And that's the equivalence classes of Z, where our equivalence relation is congruence mod n. So in the previous video, we showed that congruence mod n satisfied all the properties of an equivalence relation. So that means it gives us equivalence classes. And in fact, there are obvious equivalence classes here. We get the equivalence class of 0. So that's everything that's a multiple of n. We get the equivalence class of 1. That's everything that has a remainder of 1 when divided by n. The equivalence class of 2. That's everything with a remainder of 2 when divided by n. Ending at the equivalence class of n minus 1. That's everything with a remainder of n minus 1 when divided by n. Let's recall that those are the only possible remainders when dividing by n. Okay, so we've got n numbers here between 0 and n minus. Well, they're really n equivalence classes. And now there are some obvious operations that you can define on this. You just have to check that they're well defined. So let's define the following observation or operation on the equivalence class A and B. So A plus B will be the equivalence class of A plus B. So since we're working with equivalence classes, we have to check that this makes sense. In other words, it's well defined. And when you take an abstract algebra class, you'll see the need to do this even more and more and more. Okay, so how can we do that? So let's suppose that the equivalence class of A is equal to the equivalence class of A prime, and the equivalence class of B is equal to the equivalence class of B prime. And where we want to end, so we want to show that the equivalence class of A plus B is the same thing as the equivalence class of A prime plus B prime. So what that means is that this addition does not depend on your equivalence class representative. But let's notice if A is equal to A prime, that means that A is congruent to A prime modulo N. And then if equivalence class B equals equivalence class B prime, then likewise B is equivalent to B prime modulo N. But let's recall that means that A is equal to A prime plus N times, I'll maybe call it K, where K is an integer. That's because N divides A minus A prime by the definition of congruence mod N. And then likewise, B is equal to B prime plus N times L for an integer. Same sort of thing, N divides B minus B prime by the definition of congruence mod N. But now let's note that we can add these and we'll get A plus B is equal to A prime plus B prime plus N times K plus L. But that means that A plus B is congruent to A prime plus B prime modulo N. But that's exactly what we needed to do to show that the equivalence class of A plus B is the same thing as the equivalence class of A prime plus B prime. So in other words, this is a well-defined operation. Now we could go over here and define another operation, which is like multiplication, which would be equivalence class A times equivalence class B equals equivalence class of A times B. But we would have to check that that is well defined as well. But in fact, there's not really anything to that. It starts all the same until this step, but now you just multiply both sides of the equation instead of adding both sides of the equation. So that'll give us that A times B is equal to A prime times B prime plus N times something. And that something is a little bit complicated, and it comes from foiling out these things that I'm writing in red parentheses. But let's notice that everything other than A prime and B prime will be multiplied by N. Okay, but from there we see that A times B is congruent to A prime times B prime mod N, but that's exactly what we need for the equivalence class of AB to be the equivalence class of A prime B prime, which proves that this is a well-defined multiplicative operation. So we're going to finish off investigating some arithmetic properties of Zn. Now we're going to make an addition and a multiplication table in Z4. So that means all we need to look at is 0, 1, 2, and 3. And I'm going to use a simplified notation here, which is quite standard when working with Zn, and that's we're going to drop the brackets. Because if we know what setting we're working in, we can always think that these really mean the equivalence classes. Okay, so let's add 0 and 0. So 0 plus 0 will be 0. 0 plus 1 will be 1. 0 plus 2 is 2, and 3 is 3. And then down this line as well. Now let's do 1 plus 1, that is 2. 1 plus 2 is 3. 1 plus 3 is 4. But 4, the equivalence class of 4 is the same thing as the equivalence class of 0 modulo 4, because 4 doesn't have a remainder when divided by 4. Likewise, we can finish out this column the same way. Now 2 plus 2 is 4, but that's 0 mod 4 again, because it's a multiple of 4. 2 plus 3 is 5, but 5 has a multiple of 1 when dividing by 4, so we get a 1 there. Likewise, we get a 1 here, then 3 plus 3 is 6, so we get a 2 here because that has a remainder of 2 when divided by 4. So we get this interesting addition table when we're working in Z4. Now let's look at the multiplication table. So 0 times anything will be 0. Okay, so that's not really surprising. 1 times anything will be itself, so that's the multiplicative identity still. Now let's look at 2 times 2. So 2 times 2 is 4, which is 0. So that's actually quite interesting, maybe more interesting than you may realize at the moment, because we've just multiplied 2 non-zero objects and gotten an object which is 0. Now let's do 2 times 3. So 2 times 3 is 6, which has a remainder of 2 when divided by 4. So 2 times 3 is 2. So that's also kind of interesting. But then 3 times 3 is 9. That has a remainder of 1 when divided by 4. So 3 times 3 is actually equal to 1. So 3 is its own multiplicative identity when working in Z4. Okay, so I'm going to leave you with some warm-ups. I'm going to leave you with 3 warm-up exercises. So first, define a relation R on the integers by x is related to y if and only if x plus 7y is even. Next, prove this is an equivalence relation and describe its equivalence classes. Next, let's set A equal to the set A, B, C, D, E, and let R be an equivalence relation with 3 equivalence classes such that A is related to D and B is related to C, and then your goal is to use the properties of an equivalence relation to write R out as a set. So these two facts, that A is related to D and B is related to C, together with the fact that there are 3 classes, really restricts this down to a single type of relation. Okay, next let's make an addition and multiplication table for Z6. And that's a good place to stop.